Welcome to STR8CHEM. In this video, we're going to talk about the phase diagram for water and carbon dioxide. And to make things better, at the end of this video, we're going to try to do one example of phase diagram, and we're going to use the example of sulfur dioxide. That will be at the end of this video. So the first thing we need to look at is how to sketch the phase diagram for water and carbon dioxide. So these are the two emphases that you need to know for matriculation syllabus, and you need to be able to know how to sketch the phase diagram of these compounds. If you know how to sketch the phase diagrams of these two compounds, you should be able to do for other phase diagrams because they're going to have similar looking shapes. To sketch a phase diagram, you need to have two curves. Okay? So both of the phase diagrams over here, before you want to sketch the curves, like I said, you need to have two curves. You need to remember to have the axis. Over here will be for pressure. You can have it at atmospheric pressure or in torr or millimeter mercury. It's really up to the question. Over here, you're going to have the temperature. For now, I'm going to use degrees Celsius. Same goes to carbon dioxide. That is the axis for pressure, and that is the axis for temperature. That is the first thing you need to have in order for you to sketch the phase diagram for water and carbon dioxide, and even for sulfur dioxide later on. Okay, remember, I told you just now, the phase diagram will have two curves. What are the two curves? So the two curves you need to sketch is this. You're going to have a smaller curve down here and then a bigger one right there. Okay? Same goes to carbon dioxide. You're going to have a smaller curve and a big one going that direction. The difference now, you will see at a slope. For the water phase diagram, you're going to have a negative slope like that. Whereas for the carbon dioxide phase diagram, you're going to have a positive slope like that. This is the reason why in your syllabus, they're emphasizing on knowing these two type of phase diagrams, because you can see that in water, it has a different kind of slope, which is negative. And then in carbon dioxide, it is positive slope. Most of the compounds that we have will have a similar looking shape with what you have for carbon dioxide. Therefore, H2O phase diagram over here is a little bit unique, and we call this as the anomalous case. Later on, we're going to talk about this one. Okay? So two things that we have looked at until this point. We have looked at the axis and we have looked at the shape. For water phase diagram, the shape is like this. For carbon dioxide phase diagram, the shape is going to be like this. Remember, two curves and a slope. Water will be negative. Carbon dioxide will have a positive slope. Next, what we're going to be putting on your phase diagram is this. In the middle of that two curves and also the slope, we have a dot over there. Okay, you're going to put a dot, another dots over here. And what is that? This is going to be, remember to draw these dotted lines. That is for your T. And what is that T? That is the triple points. Very important. Okay, so the triple point for carbon dioxide is going to be right there. So what we can say here, the triple points for carbon dioxide will be at the temperature over here, which we don't know because question doesn't give it yet. But usually in examination, they will give it to you, so you don't have to worry about the data. They're going to give enough data for you to construct a complete phase diagram. But roughly, this is how you're going to sketch it. So at this temperature and that pressure, you're going to have your triple points of carbon dioxide over here. For water, it's right over there. So what is a triple point? Okay, so in examination, it's better for you to label what is T. If you're just going to simply put T, the examiner will not going to be able to know what do you mean by T. So it's much better for you to write somewhere on the side of your phase diagram T, triple points. Okay, over here. Now, next question is, you must be wondering, what does it mean by triple point? What is this triple point? So triple point, as you can see over here, okay, is a unique point. It is a unique point at which your compound, in this case, water and carbon dioxide, will be able to coexist in 3 phases: solid, liquid, and gas. Those 3 phases will exist at equilibrium at that temperature and at that pressure, the one that we have shown just now. So that is what it meant by triple points. Triple points is a very, very popular definition they will ask you in exams. So be prepared with this one. Try to memorize what does it mean by triple point. But I think it's quite easy now since you've seen the triple point over here. You can imagine that at this triple points, your carbon dioxide, your water will coexist in liquid, solid, and gas at equilibrium. So if you try to imagine that one, it's quite fascinating. It does exist. You just need to get the right temperature and the right pressure to get your water to exist in 3 phases at the same time. Okay, again, I would like to remind you, triple points is a very important definition for you to memorize. And it's not that difficult to be memorized, isn't it? Okay, next, we're going to have, apart from triple points, you're going to have another point, which is important as well, is right over here. Okay, and right over there. So that point, if we do a dotted line and going down here, okay, usually this one will not gonna exceed, just gonna stop somewhere around there. Just gonna adjust that a little bit. Drawing. Okay, so what we have here is, same goes to this. So we're just gonna stop right there. Okay. So what we have over here is this. Your critical point. So C now is a critical point. You have to label both points in your phase diagram. Triple points, critical points. Okay, you've got stats labels in your phase diagram, so you're good to go for the next one. So the next one you need to write on your phase diagram is the position of one atmospheric pressure. For H2O, the one atmospheric pressure will be above the triple points. Okay, so that is quite easy to be remembered. And down here, you will get 100 degrees Celsius. So that is another component that you need to have in the phase diagram for water. Remember, you need to label where is the one atmospheric pressure on your phase diagram. And when you go that, you're going to touch this line over here and you go down here, and that temperature right there would be 100 degrees Celsius. Whereas for the carbon dioxide, the one atmospheric pressure will be below the triple points, okay? The one atmospheric pressure for this one will be right there, and you're gonna go down here. In this case, it's okay if you don't know what is the temperature yet. It's okay. So it's just gonna be for you to know where is the position of one atmospheric pressure for carbon dioxide. If you want to know about it, usually it's going to be negative 78.5 degrees Celsius. Okay? Next, what you need to know is where is the position for solid region, liquid region, and vapor region. We have 3 regions in here. In your phase diagram. So solid will be right this region right there, and liquid will be next to it. Okay, and then vapor is going to be right here. It's going to be the same as for carbon dioxide. Solid, liquid, and vapor. So those are the things that you need to know, you need to have, you need to write on your phase diagram. A lot of students, they have difficulty to remember the position for the regions. Where is the solid going to be? Where the liquid is going to be? And where the vapor is going to be. A very good tip if you want to memorize, if you want to remember the position of the region, look at the temperature axis. Okay? So if you look at your vapor, the region for vapor mostly is going to be at a much higher temperature. So you can relate with the phenomena of having higher temperature. You're going to have vapor. Okay, vapor is going to be existing at a higher temperature, and then if you go towards lower temperature, the molecule is going to start to form liquid, and then if you cold it down further, if you have a colder region right over here at a much lower temperature, it only makes sense to imagine that your molecules right now will get closer together and they will form solid. Okay, so that's a very good tip. Try to look at your temperature over here, and if you put vapor there, think about, is it logic for you to have vapor at a lower temperature, or maybe vapor is going to be at a much higher temperature right here. Okay? Or if you do not want to use that, alternatively, you can try to remember SOLIVA. Okay? SOLIVA. So if you start from here, SOLIVA, you can remember solid, liquid, vapor, or gas. Right. So that is the first one on how to construct your phase diagram for water and carbon dioxide. So we have talked about the triple points, and you must be wondering, what does it mean by critical points? So this is basically the definition of critical points. So what you need to know over here, at the critical point, beyond critical point, it is not possible for you to liquefy gas molecules, no matter how high the pressure you're going to put, no matter how high you're going to go up to the pressure, you cannot liquefy your gas molecules even further. So at that point, you're going to have a supercritical fluid. Okay? So you don't have to worry about that. You just try to remember what's going on over here. And remember, just now I've told you the most important one that you need to remember, and the most fundamental is this, triple points. Okay? This one is also important, but don't worry so much about memorizing. The more exercise you can do, the better you will get. Okay. Now, so over here we have the phase diagram for H2O. And what we're going to try to look at now, we're going to try to get to know the lines. We have the two. If you look here, we have this boundary, okay, TA boundary, TC boundary. T is the triple points, C is the critical points, and we have the TB boundary. So what are these boundary? So if you look over here, TC denotes the vapor pressure curve of liquid, or alternatively, you can call this as the liquid-vapor equilibrium curve. Okay? And then at TA, if we look at TA over here, that one is the vapor pressure curve of solid, or you can call it as the solid-vapor equilibrium curve. Right? And if you look at TB, that line here, that is the solid-liquid equilibrium curve. So what does it mean here? If your pressure is going to be touching at this equilibrium curve, and your temperature is going to be over here as well, that means your water right now exists as a vapor. Oh no, it's as a liquid, as a liquid and as a solid when you touch at that line over here. If you touch this line over here, if you get a temperature at 100 degrees Celsius, like in this example, and then you have 1 atmospheric pressure, this is when your water will exist as liquid and vapor in equilibrium. So that's why you have it boiling. When you have your water to be boiled at 100 degrees Celsius at 1 atmospheric pressure, that's why you're going to start to see all the bubbles coming up, because right now your H2O exists as liquid and gas at equilibrium at that pressure, at this temperature right over here. Okay, so this is the anomalous behavior of water. Why does, if you remember just now, why does water has slopes to the left? So the answer for that one is this. So that is simply the answer that you should write in exams. Because ice is less dense than water, you need to remember ice over here is solid H2O. And then water over here refers to liquid H2O. Because solid H2O is less dense than liquid H2O. As you can see over here, you can see that the solids are floating on your liquid. So that is the reason why your water phase diagram will have a negative slopes or sloping to the left. Okay, now let's have a look at the phase diagram for carbon dioxide really quick. So as you can see, we have the same shapes of the phase diagram, but for carbon dioxide, you have a positive slope. For TB curve over here, that is what we call as the solid liquid equilibrium curve. Okay, and then for the TC, that is what we call as the liquid vapor equilibrium curve. And for the TA, yes, that would be solid vapor equilibrium curve. Okay? So what you see here, the sloping to the right for carbon dioxide is a typical sloping. Means for sulfur dioxides and methane, other examples for phase diagram, they're going to have a typical right sloping or positive slope for the phase diagram. Okay, so at the triple points, that is the temperature and pressure for carbon dioxide. You can have a look at this one. So the most important part over here is this. The triple point is above atmospheric pressure. So that is a very, very interesting point, the one that we have drawn just now. So what is the impact of having the triple point above atmospheric pressure? Atmospheric pressure is the pressure that we are experiencing at room temperature, slightly above sea level. So when you have that phenomena over here, that is the reason why carbon dioxide will exist as dry ice. So this is dry ice here. So what does it mean by dry ice? So this ice, if you have it in your hand right now, it will not gonna melt like normal ice that you have in your fridge. If you have water ice, water solids, if you leave them, the ice cubes in your room, they're gonna melt to become liquid first, and then slowly they will evaporate to become vapor. But for carbon dioxide, because the triple point is above the atmospheric pressure, you will not gonna see this carbon dioxide solid gonna go through the liquid phase. So they're gonna sublime, directly changes to gas. Now we're gonna look at a typical examination question for phase diagram. So over here, what the question one is, the question wants you to sketch the phase diagram for sulfur dioxide. And if you read the question further, it gives you a few information that you need to include in your phase diagram. You need to, first of all, you need to have your triple points, which is going to be at 198 Kelvin and 1.0 times 10 to the power of negative 3 atmospheric pressure. That is a triple point. And of course, you're going to have your critical points at the temperature of 430 Kelvin and at that pressure, 78 atmospheric pressure. Two other information you need to include is the normal melting point and normal boiling points, which is going to be at 200 Kelvin and 263 Kelvin respectively. So when the question says normal over here, that refers to pressure equals to 1.0 ATM. Okay, so we need to be able to do A first to sketch the phase diagram before we would be able to get to B and C. So, as usual, what you need to have the axis for pressure right over here, and you need to draw the axis for temperature right over there. And remember, in the question, the temperature will be in Kelvin, so you're going to put K, and the pressure will be at atmospheric pressure, so you're going to put ATM. The first thing we need to do, we need to draw the two curves. So you have small curve and the big curve, okay? And then we're going to draw the slope. So for the slope of SO2, it's going to be a positive slope like this, just like carbon dioxide. Remember, negative slope only for H2O. So for sulfur dioxide, you're going to have a positive slope like this. The first thing we need to identify or to put in your phase diagram here is the triple points. The triple point will be at 198 Kelvin and 1.7 times 10 to the power of negative 3 atmospheric pressure. So over here, it's going to be your triple points. Okay, so that is your triple point. So down there, that is 198 Kelvin. And then the pressure is right over here. That should be about 1.7 times 10 to the power of negative 3. Okay. And then next, what you need to identify is the critical point, which is going to be at 430 Kelvin at 78 ATM. So that should be right over here. That is 430 Kelvin. Okay, so that is your critical point. And then the pressure would be about 78 atmospheric pressure right there. So we have done for the triple points and we have done the critical points. Remember, always label what does it mean by T. So T over here refers to your triple points, and C refers to your critical points. The other two things we need to identify or put in your phase diagram for sulfur dioxide is the normal melting point, okay, normal melting point and boiling points. That is the temperature for melting points and 263 Kelvin for your boiling points. Okay, so 200 Kelvin is for your normal melting points. 263 Kelvin is for your normal boiling points. And like what we have talked about just now, when they say normal, that refers to pressure equals to 1.0 atmospheric pressure. And we can start doing, I'm going to use that color just now. Okay, so for melting point is about 200. So let's say 1 atmospheric pressure is going to be just right there. Okay, so let's say the 1 atmospheric pressure is just right there. So if we're going to draw that line, so when that touch this boundary, so that is the boundary for, remember, this one is your solid, this one is for your liquid, and this boundary, this region over here is for your vapor. So when you touch this point there, that is the equilibrium between liquids and vapor. So that's when you're gonna start to boil. So the boiling point will be at that equilibrium. Here would be your 263 Kelvin. Okay, and then when you touch that point there and you go down here, that temperature over here, which is 200, that one would be your melting point. So at this equilibrium right now, at the solid liquid equilibrium, when the temperature is touching there and the pressure is touching there, this is when you're going to start to have your SO2 to melt. Okay, so the melting point is right there. That is the melting points. Okay, now we have done for this. We have done for A. What about B? B wants you to state the changes in phases if SO2 is cooled from 220 Kelvin. Okay, so let's say 220 Kelvin is somewhere here, 220, and we want to go for 160. So what are the phase changes? So to do that, I'm just gonna rub this off because I'm gonna write something there. Okay, so the other important keyword over here is at constant pressure 1 atm. So we're gonna refer to, I'm gonna use yellow for B. Now I'm gonna use yellow. So you're gonna look at that temperature and that temperature. So we want to go, okay, so we want to go from here. So we're gonna start at 1 because they want you to state the changes in phases. They want you to state the changes in phases when the pressure is 1 atm, which is here, and then you're gonna go and cool it down until you're gonna reach this temperature right there. Okay, so now you have point number 1. So let's say this is 0.1 Roman for B. So 1 Roman. At 1 Roman, what is the phase? That is going to be liquid. Okay, so this one is at 200, liquid at 220 Kelvin at this point I. So when you move, you're gonna touch here, right? So at point 2 right now, this is point 2, which is the melting point. What will be exists? So what you have here, you're gonna have the solid, liquid, equilibrium. Okay, you have the temperature maybe around 200 Kelvin. So when you move, so now you have moved there. Now you're going to move to that point. So this is, let's say, point 3 Roman. So 3 Roman, that one would be in this region, which is solid at 160 Kelvin. So that's how you're going to answer question number B. Okay? So when you look at C, it's slightly similar. Okay? It's quite similar with what you have doing with what we have done for part B. So I'm going to use black now, okay, for C. So when you look at C, it wants you to state the changes as well for SO2, but this time you can do it isothermally. Okay, so before I'm going to continue, I'm just going to introduce you. When it says isothermal, that means you have constant temperature but different pressures. Okay, another term is isobaric. If you have isobaric, that means constant pressure but different temperatures. Very, very important two terms. Okay, remember, isothermal, you have constant temperature but different pressures, so you're gonna changing the pressures. Isobaric, you have constant pressure but different temperatures. Therefore, if you look at question B over here, this is an example of isobaric question because you have constant pressure but you are changing the temperature. What about, we're going to look at C. How are you going to do that? So you're going to use the same technique. What we're going to do now, you have the temperature 350. So let's say 350 is right there. Okay, so you have 350 right over there. And then they want you to change from 0.5 atm to 4 atm. So 4 atm, so let's say 4 atm is right over here. Okay, so that is 4 atm from 0.5. 0.5, maybe it's just going to be right there. So that is 0.5. Okay, so that is 4. Okay, 4 atm. And then 0.5 right over here. So 0.5. So that is 350. So 350, they want you to state the changes. Okay, so what are the changes now? For isothermal, look, the temperature will be the same, 350. If for isobaric, we are moving that direction. For isothermal, you're going to go up or you're going to go down. Okay, so the temperature is going to be the same. Okay, so what we going to be doing now, you're going to start from here. Okay, so let's say this is, okay, isobaric, and then that is somewhere around there. So that is 0.1 right now for C. Okay, if you look here, 0.5, we start there at this temperature. So that is 0.1. You want to go to this point right there, slightly that point. Okay, slightly out of that point. So you have 1, and then you have 2, and then you have 3. Okay, phase changes. So at number 1, what happened? It will be, look at this number 1, where is the region? The region is vapor. It will be vapor at 0.5 atm. Remember, right now we are doing for part C. And then 2. Okay, point 2 is when you are touching that equilibrium line. Remember, this is the liquid-vapor equilibrium. So number 2, so you're going to start to, that is essentially a boiling line. Okay, so that is boiling point. So that will be the liquid vapor equilibrium at this. So we don't know the pressure, so you don't have to worry about that one. I'm just gonna write the liquid equilibrium. That should be fine. And then the third one over here, the third phase, is liquid. Okay, look at this. The third dots there, this is number 1, 2, 3. The third one is in the region of liquid, so it will be liquid at 4 atmospheric pressure. So that's how you're going to answer question about phase diagram. It looks quite messy right now, I know, but when you try to rewatch this video, you try to draw a much bigger structure, it's going to be easier for you to look at.